Hello dear students, in this video we will discuss about rheology. So this topic come under the physical pharmacy, right? So first we will try to understand the basic things. Here we have the rheology, the disyllabic word. One is the rheo we have, other one is the logos. What is the rheo? Yes, the rheo means it is the flow. What do you mean by logos? The logos means science. So in the rheology, what we are going to study? We are going to study about the flow of science. What is that we are studying? Here we are studying about the flow of science. But which scientist was said the term rheology? Who is that scientist? The name given the rheology. Yes, the name of the scientist here we called Bingham. So this is the scientist. He has given the name what? Rheology. And what do you mean by rheology? It is the flow of science. Let me take the two liquids here. So here I have taken this is the one liquid. This beaker, there is a one liquid is there. And in this beaker, there is another liquid is there. Okay. So the first beaker, A beaker, and the second beaker, B beaker. Here the two beakers are there. In these two beakers, liquids are there. Okay. Now what I did, here I applied the stress. What do you mean by stress? The stress means the force I have applied. Here also I applied the stress. The stress means force I applied. Now I asked the question, can you tell me where will be the more movement? Where will be the more movement? When I applied the force? The same force, that is the same stress I applied. Yes, here I observed that more movement. Here I observed that more movement. The more movement means there will be a flow. The liquid start flowing now. But here I observed the flow is less. Here I observed the flow is less. Can you tell me why here flow is less? Why here flow is less and why here the flow is more? Yes, the reason is in this A beaker, whatever the liquid we have, this liquid is the viscous. This liquid is the what? Viscous. Due to viscous liquid, the flow is less. Right? Due to viscous liquids here, the flow is less. I can say here the person is the chubby. That's why the movement is very less. He cannot able to move. And here the person is the not chubby. That's why the movement is very good. So whenever the liquids we are having the viscous nature, their flow is what happening? The flow is more or the flow is less? Obviously the flow is less. Whenever we have the viscous liquids, the flow is less. Why the flow is less? Because there is a resistance. There is a resistance. The liquid, it is showing the resistance to move. The liquids, it is showing the obstacles to move. That is what we say it as here, viscosity. Okay. So the two things are very clear. One beaker I have taken the thick liquid, other beaker I have taken the thin liquid. Now in this both condition, I applied the force, I applied the stress. Here the movement is less, the flow is less. Here the movement is more, the flow is more. Okay. Now whenever the viscosity increases, the obstacle also increases, the movement will decreases. If the viscosity increases, movement is what happening I am saying? Movement or flow is decreases. If the viscosity increases, resistance is what happening? Yes, resistance is increasing. That's why here the movement or the flow is less. That is what the basic things about the resistance and flow. Now, here what I am having, here I am having the two liquids. Let's say that this is the one liquid and here I am having the another liquid. Here I am having the another liquid. Okay. Now, to this liquid, I applied the force. Here the force, technically we call it as the shear stress. We are applying the shear stress. That means force we are applying, we designate the symbol is the F. Okay. Technically what we say that one, shear stress. That means force only. Now what I did, I applied the force now here. How much force or how much shear stress I applied? I applied the 5 Newton shear stress. That was the 5 Newton F I have applied. When I applied the 5 Newton shear stress, the flow I found 5. When I applied the 10 Newton shear stress, the flow I found 10. The 20 Newton shear stress, the flow is the 20. That means what is happening? The shear stress I keep increasing. When I keep increasing the shear stress, the flow also increasing. What is the shear stress we say? F. When the shear stress is increasing, the flow also increasing. When I keep increasing the stress, the flow also increasing. Here the flow we designate that rate of shear. The flow means here understand that rate of shear. In simple format, we say it as the flow rate of shear. The F directly proportional to G. What is the G? The G is the rate of shear, the flow. Okay? Increase the shear stress, the flow is increasing. But did you observe? It is the proportionally increasing or not proportionally increasing? Yes, proportionally increasing. 5 Newton, 5. 10 Newton, 10. 20 Newton, 20. The proportionally increasing the flow. Okay. So, if the liquids are showing the flow this way, that liquids we say it as the Newtonian liquids, or that flow we say it as the Newtonian flow. This type of flow, what we say? Newtonian flow. The shear stress increasing and flow also increasing. This type of the flow we say it as the Newtonian flow. Okay. Now on the other hand, I have taken the other liquid, other fluid. This fluid, what I did, I applied the 5 Newton force. Zero flow. There is no flow. Okay, let me increase the force now. Shear stress. 10 Newton force. Again, zero flow. I applied the 30 Newton force. Yes, there is a 3 flow. And I applied the 14 Newton flow. Yes, there is a 5 flow. I applied the 15 Newton force. I found that 8 flow. Did you observe one thing? What is that? What is that? 5 Newton, 0 flow. 10 Newton, 0 flow. But 30 Newton, the flow is the 3. 14 Newton, the flow is the 5. And the 15 Newton, the flow is the 8. But can you tell me here? Can you tell me here? The flow is the proportional increasing? When I am applying the shear stress, is that force is, when I am applying the shear stress, the flow is proportionally increasing? Answer is no. Look at here. In the first condition, the flow is increasing proportionally. Here the flow is not increasing proportionally. Okay, the rate of shear is not increasing proportionally. What is that? You increase the shear stress, but the flow is, or rate of shear is not increasing proportionally. Not increasing proportionally. Okay, so shear stress is increasing, but rate of shear, flow, G, not increasing proportionally. So this type of the flow, we say it as the non-Newtonian flow. Non-Newtonian flow. Now clear, we have the two types of the flows. One is the Newtonian flow, other one is the non-Newtonian flow. The Newtonian flow means, yes, shear stress directly proportional to the rate of shear. In the non-Newtonian flow, shear stress is not directly proportional to the rate of shear. Means the force if you increase, the rate of flow is not increasing proportionally. The rate of shear is not increasing proportionally. So that is what Newtonian flow and non-Newtonian flow. Okay. So now the more in details we will talk about this one. Let's say this is the one beaker. This is the other beaker. This beaker I am having one dispersion. Okay. In this beaker, I am having the dispersion. But what was the condition? In the A condition, I am having the 50%, I am having the 80% of the solid and 20% of the liquid I dispersed. On the 80% of the solid, 20% of the liquid is dispersed. In the B condition, what I did, I have taken the solid 50%, I have taken the liquid also 50%. Solid and liquid 50%, here the both are the miscible. Now it becomes the miscible. The miscible means there is a formation of the saturated solution. Solid and liquid, the both are the equilibrium. In the first condition, 80% of the solid, understand, and 20% of the liquid, the both are not equal. So what we applied here, we got some immiscibility, or you say it as the, here we call it as some not dissolved. They both are not dissolved or immiscibility. Okay. So that was the first condition, that was the second condition. Now I asked that in the both condition shear stress is applied. Here also I applied the shear stress. Here also I applied the shear stress. Can you tell me which one will flow faster? Which one will flow faster? Your answer is A. Is it your answer is A? No. It is not A. If you are answering A, it is a wrong answer. It is the B. The B will flow faster. Why? Why the B will flow faster? Because there is a miscible. Miscible means whatever we got the beaker, in this beaker we have the single system, that is the homogeneous system we have. Here we are formed the homogeneous system. Can you tell me, in the A beaker, do we got the homogeneous system? No, it is not homogeneous system. I have already given the condition. What is the condition? In the A beaker, 80% solid, 20% of the liquid. The both are the not soluble. That means we got the two phases here. That's why this we call it as the heterogeneous system. We call it as here heterogeneous system. This is the heterogeneous system. This is the homogeneous system. Okay. Here there is a solubility. Here there is a no solubility. Here there is a no solubility. Due to less soluble, more solid content. Due to more solid content, the flow is decreased here. Here the flow is decreased. But here flow is the more. Here the flow is the more. The simple format if I want to say, what was that? Which system shows the non-Newtonian flow? The A or B? Which system shows the non-Newtonian flow? A or B? Not answer B, Answer is A. Here A can shows the Newtonian flow and B can shows the non-Newtonian flow. A can shows the Newtonian non-Newtonian flow, B can shows the Newtonian flow. So the solid content is more and the flow is not good. That means if you applied the stress, if you applied the force, the flow is not proportionally increasing. 20 Newton if you applied, the flow you might absorb 5 flow. 30 Newton if you observe, the flow might you can see 8 flow. 14 Newton you can apply, the flow might you can see that was the 11 flow. It is not increasing proportionally, but here increasing the flow proportionally. So finally we conclude which system will shows the non-Newtonian flow, which system will shows the Newtonian flow. Can you tell me which system showing the Newtonian flow? Homogeneous system. Can you tell me which system showing the non-Newtonian flow? Yes, heterogeneous system. Heterogeneous system, non-Newtonian flow. Homogeneous system, Newtonian flow. That is what the, on basis of the system, how we can divide the Newtonian flow and non-Newtonian flow. Okay. Now, the more in detail about the non-Newtonian flow, we will discuss now. Okay. The question is, in the pharmaceuticals formulations, where we will get the heterogeneous system. That means, where you can absorb the immiscibility, or where you can absorb the not dissolved system. Can you tell me? Where we can absorb the immiscibility? Obviously, when we have the oil phase and water phase, then there will be a immiscibility. The immiscibility means heterogeneous system. So, in which formulation having the oil and water? Right. It is the O by W or W by O. What is that? Emulsions. In which system we are having the oil and water? That was the emulsions. Now you say, is that emulsions will shows the Newtonian flow or non-Newtonian flow? Answer is emulsions will shows the non-Newtonian flow. Okay. Now tell me, in the pharmaceutical formulation, where you can see the not dissolved? Not dissolved means there is a solid particle, there is a liquid one. When the solid is dispersed in the liquid, then when the solid is dispersed in the liquid but completely not miscible, the solid is not completely dissolved in the liquid. That's why we say it as the not dissolved. Yes, where you can see this condition? Right answer, you can see this condition in the suspension. You can see this condition in the suspension. So, suspensions will exhibit is the what type of the flow? Again, answer will be non-Newtonian flow. Is there any other example? Even colloids also. Right? Colloids also shows the non-Newtonian flow. And ointments also shows the non-Newtonian flow. These are the best example for the non-Newtonian flow. Whether it is the immiscible or insoluble solid content is there. In the system, insoluble solid content is there. In these all systems, if you applied the shear stress, the rate of shear is not increasing proportionally. The both are not proportionally. 10 न्यूटन अप्लाई करने के बाद आपका 10 फ्लो नहीं आएगा. 20 न्यूटन अप्लाई करने के बाद you don't get the 20 flow. The proportionality you cannot observe here. What are the systems? The system which is the immiscible. Example, emulsion. The system which is having the insoluble solid content. Suspension, colloids, ointment. Finally, Non-Newtonian flow follows suspension, emulsions, ointments and colloids. These are the best example for the non-Newtonian flow. These are the best example for the non-Newtonian flow. Okay? All of them clear? Now, the more in detail about the non-Newtonian flow, we will try to read it. Okay? Let's see that. What we are talking here. This is the solid or the fluid I have. Okay? Now, here what we have. I am taking the micro direction here. Micro particle I am taking. The two particle I have taken. And I observed under the microscope. Once I observed under the microscope, I come to know there is a interaction between the one particle to other particle. There is an interaction between the one particle to other particle. This interaction having the strong interaction. Strong interaction. There is a one more two particle. These two particles also I observed. Here also there is a strong interaction. Okay? The two particles having the strong interaction. Now, will they flow faster? These fluids, will they flow faster? Answer is no. They don't flow faster. But when they can flow faster now? Yes. When you break this bond, they becomes the individual. When you break this bond, they can becomes the individual. When they becomes the individual, then they start flowing. When they becomes the individual, then they start flowing. Now, if I want to break this bond, let's say that I required the 30 Newton force. Let's say that I have taken the hypothetical value 30 Newton force I required. That means the shear stress I required here 30 Newton. If the 30 Newton shear stress is there, then I can break this bond. After breaking this bond, the particle becomes the individual. When the particle becomes the individual, they can flow. They can flow. Okay? Now what I did here, initially I applied the force to this liquid, this dispersion. How much I applied? I applied the 5 Newton. There is no flow. I applied the 10 Newton. There is no flow. I applied the 20 Newton. There is no flow. But I applied the 30 Newton. The flow is started now. The flow is started now. Because after 30 Newton, at 30 Newton, the bond is broken. Then the flow is moved. Then flow is started now. But initially, the flow is not there. If I draw the graph between the shear stress, that is the force, rate of shear, that is the flow. When I draw the graph, then how I will get here? Look at. This is the x-axis and this is the y-axis. On the x-axis, shear stress, which indicates the F. On the y-axis, rate of shear, that indicates the G. Let me take 0, 10, 20, 30, 40, 50, 60 and so on. Okay? I started the shear stress 0. 0 say 10 Newton, the flow is not there. 20 Newton apply किया, flow is not there. 30 Newton apply किया था, yes. At 30 Newton, at this point, the bonds are broken. The interaction was broken. When the interaction is broken, after this, start moving now flow. Now the flow is started. Initially, there is no flow. Initially, there is no flow. But after 30 Newtons, the flow is started now. After 30 Newton, the flow is started now. Okay? In this graph, initially there is no flow, but after 30 Newton, the flow is started. Before 30 Newton, here the material behave like a elastic nature. There is a elasticity. There is a elasticity like a spring. They behave like a spring way. but not able to break. But for breaking the bond, we required the 30 Newton. After this 30 Newton, they start moving now. There is a mobility, there is a movement now. Okay. Now, this 30 Newton, we call it as the yield value. What is the yield value here? The force required to break the bond. The force required to break the bond between the two particles. That we call it as the yield value. Before yield value, this portion is the before yield value, and after yield value is the this portion. This is the before yield value, and this is the after yield value. Remember, in the before yield value, the flow is not there. After yield value, the flow is started. And if the material showing this type of the flow, we say it as the plastic flow. This type of the flow, plastic flow. Now tell me, plastic flow is the Newtonian flow or non-Newtonian flow? Answer is the non-Newtonian flow. Why? You applied the 10 shear stress. Is there any flow? No. You applied the 20 shear stress. Is there any flow? No. But when you applied the 30, after 30 it start moving that. There is a no proportionally increasing. That's why this flow we say it as the plastic flow. This plastic flow also we say it as the Bingham flow. And the material shows the plastic flow, we call it as the Bingham body. What do we call this one? Bingham bodies. Which is the Bingham bodies? This is the Bingham bodies. These are the Bingham bodies. These materials are showing the plastic flow here. These materials we say it as the Bingham bodies. What we say here? Bingham bodies. But did you observe one important thing? After yield value. एक बार ध्यान से ग्राफ देखा तो आफ्टर यील्ड वैल्यू हाउ दे आर हियर 10, 20, 30, 40, 50, 60. Okay, so what is that? I applied the 30, the flow is the 30, yes, shear stress is the 40, the flow is the 50, and shear stress is the 50, and the flow is the 60, and the shear stress is the 60. Means what you observed is that after yield value increasing proportionally or not increasing proportionally? There is a increasing the proportionally. 40 का 40 मिला, 50 का 50 मिला, 60 का 60 मिला. मतलब after yield value the flow is behave like a Newtonian, because there is a proportionally increasing now. The shear stress and the shear rate, the shear stress and the shear rate of shear, the both are proportionally after yield value. That's why after yield value, this is behave like a Newtonian flow. This is behave like a Newtonian flow. And before yield value, they are behave like a non-Newtonian flow. They behave like a non-Newtonian flow. You can see very clearly before yield value non-Newtonian flow, after yield value Newtonian flow behaving. So that is what the important characteristic about the plastic flow. Important characteristic about the plastic flow. Okay. But in the GPAT, other than this concept, what is important? Slope. In the plastic flow, what is the slope? The slope here we say it as the plastic viscosity. The slope is in the plastic flow we called plastic viscosity. We represent the symbol U. The plastic viscosity represents the symbol U. The U means it is the reciprocal of flow only. Reciprocal of flow. Flow means mobility. Mobility. So U inversely proportional to the mobility. That means the plastic viscosity increases, mobility is decreases. When the plastic viscosity decreases, mobility increases. Obviously, viscosity decreases, mobility always increases. That is what the slope here we are getting u. What we are getting here, the slope is the u. Okay? Everyone clear? The reciprocal of mobility, we say it as the plastic viscosity. Okay? Now my question is, what are the Bingham bodies here? Means, which materials will shows the plastic flow? Did you observe? In the dispersion, one particle to other particle is aggregated. One particle to other particle is fused here. Now can you tell me, in which suspension the particles are aggregated? You all are aware, in the suspension we have the two types. One is that flocculated suspension, other one is the deflocculated suspension. Can you tell me where the flocculi is occurring? Yes, in the flocculated suspension, there is a fusing between the one particle to other particle. There is an interaction between the one particle to other particle. In which suspension? Flocculated suspension. What about deflocculated suspension? Obviously, name itself is the deflocks. There is a no flocks, there is a no adherence between the one particle to other particle. But in the flocculated suspension, adherence is there. Okay. Now you tell me, plastic flow shows the flocculated suspension or deflocculated suspension? Answer is the flocculated suspension, because this is the flock and there is an interaction. Now we need to break this interaction. Then this will start flowing. That's why flocculated suspension is the best example for the plastic flow. The example for the plastic flow, flocculated suspension. This is the very, very important thing. Other than this, some semi-solids, like, you know that in the semi-solid, there is a cross-linking of the polymers. This is the one polymer and this is the other polymer. This is the one, this is the one, this is the one, this is the one. Now, this entire system we call it as the polymer. And this one we call it as the monomer. How the polymer it forms? The cross-linking of one monomer to other monomer. Cross-linking of one monomer to other monomer. That we call it as the polymer. And in the suspension, there is a cross-linking of the polymers we are using for increasing the viscosity of the system. Now tell me, if you need to break, you require some force. If you break this force, if you break this bond, then the flow will start. That's why the semi-solids are the other example for the plastic flow. Semi-solids are the other example for the plastic flow. Okay, so that is what all about our system plastic flow. Very simple to understand. Plastic flow, initially there is a no flow, but after yield value they start behave like a Newtonian flow. For breaking the bond, we required some force. That force we say it as the yield value. Okay, when you break that bond, then they start moving. After yield value, Newtonian flow. In the plastic flow graph, the right hand side indicate is the Newtonian flow. And the left hand side indicate is that non-Newtonian flow. Okay, so this type of the behavior we say it as the plastic flow. Okay, everyone very, very clear? Very good. Now we will move to the second type of the system. Here I am having the dispersion. But this dispersion, I applied the shear stress and rate of shear. Shear stress I applied the 10 Newton. But In fact, I observed the flow 2. Let's say example. I applied the shear stress 20 Newton. I observed the flow 3. I applied the shear stress 30 Newton. I observed the flow 5. I applied the shear stress 40 Newton. The flow is the 8. The flow is the what? 8. And I applied the 50 Newton. The flow is the 11. Did you observe? In this system, this material, how they are behaving? I applied the 10 Newton, flow is the 2. I applied the 20 Newton, flow is the 3. I applied the 30 Newton, flow is the 5. I applied the 40 Newton, flow is the 8. 50 Newton, 11. 2 to 3, the gap is the 1. 3 to 5, the gap is the 2. 5 to 8, gap is the again 3. Are you getting my point? And 8 to 11, the gap is the 2. Did you observe? Is there increasing proportionally? 1, 2, 3, 2. Increasing proportionally? No, it is not increasing proportionally. When the force is applying, the proportionally the flow is not getting. Can I say non-Newtonian flow? Can I say non-Newtonian flow? Yes, this is a material also non-Newtonian flow now. This material also start behaving like a non-Newtonian flow. But if you look at very carefully, at a 10 Newton, are we getting any type of flow? Yes, we are getting 2 flow. There is a flow. There is a flow at initial shear stress. There is a flow after 20 Newton also. But when you see the before example, when you see the plastic flow, at a 10 Newton, there is a no flow. At 20 Newton, there is a no flow. But at 30 Newton onwards, they are showing the flow. They are showing the flow. Did you observe here any kind of the Newtonian behavior? Did you observe any Newtonian behavior here? No, we don't observe any Newtonian behavior here. There is no proportionality of increasing here. Flow is not proportionally increasing here. But the graph initially it is starting the flow. Initially it is showing the flow. That means what you can see here, this is the shear stress F. This is the rate of shear 0, 10, 20, 30, 40, 50, 60. Now I applied the 10, the flow is increased the 2 very less, and I keep increasing the shear stress, the flow is slowly increasing. The flow is slowly increasing. But the flow is not proportionally increasing. We don't get the linear graph. We don't get the linear graph here. Okay? Can you tell me, do we have any type of in this system, do we have any type of the yield value? Do we require any type of the yield value? Answer is no. Not required the yield value here, because the first shear stress only it is showing the flow. At a 10 Newton itself, it is start doing the flowing. So there is any kind of the yield value in this system, because one particle to other particle, there is no connection actually here. There is no connection between the one particle to other particle. That means there is no aggregation here. There is no flux here. They are not connected. They are what? Not connected. But what is happening, when you increases the shear stress, the viscosity is decreases. If the viscosity is decreases, the flow is gradually increases. The flow is gradually increases. Okay? Everyone clear? Everyone clear? So this is what the one type of the flow we say it as the pseudo plastic flow. This type of the flow we call it as the pseudoplastic flow. What was that? Pseudoplastic flow. The pseudoplastic flow, the graph is passing through the origin. Remember, graph is passing through the origin, but there is a no yield value. But there is a no yield value. The graph is passing through the origin. The graph is passing through the origin, but there is a no yield value. The graph is like this. It is passing through the origin, but no yield value here. But in this rheogram, we can observe the two types of the segments. One is that first order segment. Other one is the zero order segment. These both segments we can see. One is the concentration dependent, and after some time not concentration dependent. The both type of the segments we can see here. Okay. And what type of the material will show pseudoplastic flow? What type of the material will show pseudoplastic flow? Example, natural and synthetic gum. Natural and synthetic gums. You know what is the natural gums? Yes, it is the tragacanth. Natural gum, natural binder this is, and sodium alginate, and methyl cellulose, and sodium carboxymethyl cellulose. These are the synthetic gums. So these are the example for the pseudoplastic flow. These polymeric solution will shows the pseudoplastic flow. Okay, this is, remember, solution. That's why there is a flow starting only, but not greater flow, but there is a little bit flow. There semi-solid. That's why initially there is a no flow. Solid, initially there is a no flow. Did you understanding what I am saying here? In the plastic flow, solid, semi-solids. We are using the polymer, but that is a semi-solid. That's why zero flow initially. This is the solution. There is a flow initially, but not great flow. Some little bit flow is there here. So this is what the example for the pseudoplastic flow. Pseudoplastic flow. My question is, when the graph is the not straight line, you know that the graph is the not straight line. We know when the graph is the not straight line, can we determine is the accurate values? Can you find the accurate values? Pseudoplastic viscosity, pseudoplastic flow, can we determine accurately? The answer is no. The answer is no. Now what is the solution? Yes, we want straight line. If you get the straight line, then only you can find it. So for making the straight line, regularly what we do? In the graph, that is the shear stress and the rate of shear. To get the straight line, what we do? Yes, many times we have discussed, we take the logarithms. Here we take the log shear stress, we take the rate of shear is the log G. So we will get the equation log Z equal to N into log F minus log eta. Log eta. Are you getting my point? So here what is the N here? The N is here. Yes, it is the number. That is the how much shear stress you are applying. 1, 2, 3, 4, 5. How much shear stress you are applying. So that after this become the number of shear stress, on this basis only the flow will be there. Okay. So the basis of the number of shear stress, the flow will be there. F is the shear stress. Okay. So that is what the, by taking the logarithm, we will get the graph is the straight line. Okay. So this is what the pseudoplastic viscosity. What is the pseudoplastic flow here? The initially there is a no flow. Initially there is a no flow? No, initially there is a flow here. In the plastic flow, initially there is no flow. In the pseudoplastic flow, initially there is a flow, but not a greater flow. Okay. Now we will move to the third type of the system. What is the third type of the system? I have taken the material. Okay. This is I dispersed here. I applied the shear stress. After applied the shear stress, what is happening? What is happening here? The molecules behave like this. The molecules behave like this. How they behave? Did you observe one thing? After applied the shear stress, whatever the particle we have, these particles are the dilated now. These particles dilated. Dilated means the volume is increased now. After shear stress, the volume is increased now. That's why this flow we call it as the dilatant flow. This flow we call it as the dilatant flow. In the dilatant flow, what is happening? We applied the shear stress, then the system volume increases. System volume increases. In the dilatant flow, when you applied the shear stress, the system volume increases. Okay? But what about the pseudoplastic system? What about the pseudoplastic system? Yes, exactly opposite to the dilatant flow. Always remember, pseudoplastic and dilatant flow, the both are the opposite. The both are the opposite. They are the opposite. How it is a opposite? In the pseudoplastic system, when you apply the shear stress, the viscosity, when you apply the shear stress, when you increase the shear stress, viscosity is what happening? Viscosity is decreases. In the dilatant flow, when you increase the shear stress, when you apply the shear stress, viscosity is decreases. The both are the opposite. Viscosity is what happening? Decreases. That's why dilatant. That's why dilatant. No, it is not viscosity decreases. Here the viscosity is increases. I said opposite, right? Then how they get the opposite? This is the decreases means this is the increases. That's why where the students do the mistake. Remember, this is where the students will do the mistake. What is the thinking about the dilatant flow in the students perspective? Dilatant means flow हो रहा है, viscosity कम रहेगा. Wrong perception. Wrong perception. The viscosity increases here. The volume increases, but the viscosity increases. Viscosity is what happening? Increases. Why? When you applied the shear stress, the particles are becomes the closer now. Initially the particles are individual, but after applying the shear stress, here the particles becomes the closer. The particles becomes the closer means what is happening? Adhered now, the viscosity will be more now. The viscosity will be more now. Initially deflocculated. This is the deflocculated system. But once you applied the shear stress, one particle to other particle adhere now. They behave like a flocculated way, but not flocculated system. It is the deflocculated system only. Are you understanding? That's why I said viscosity increases. When the particles are adhered together, viscosity increases. But volume is increases, viscosity is increases. Here, volume and viscosity is increases. It is very simple. The difference between the pseudoplastic flow and the dilatant flow. In the pseudoplastic flow, increase the shear stress, viscosity is decreases. In the dilatant flow, increase the shear stress, viscosity is increases. Here viscosity decreases, here viscosity increases. Viscosity increases. That's why we call it as the shear thickening system. This we call it as the shear thickening system. This we call it as the shear thinning system. Why we call it as the shear thinning system? Because viscosity is decreases. Why we call it as the thick? Because viscosity increases. Now the graphs also opposite. Can you tell me what is the graph we drawn? F, G. In the pseudoplastic system, what is the graph we drawn? This is the graph. Opposite means the graph will becomes the opposite now. Yes, the graph will be what it will comes now? Like this. Like this. Opposite way. This is the graph of the dilatant flow. This is the graph of the pseudoplastic system. And what is the plastic system graph? Yes, the plastic system graph. This is the plastic system graph. Graphs are very clear. The both are the opposite. Dilatant flow, always remember, again I am more stressfully saying, in the dilatant flow, viscosity increases after applying the shear stress. Okay? And in the pseudoplastic system, after applying the shear stress, viscosity is decreases. That's why dilatant flow we say it as the shear thickening. Pseudoplastic flow we say it as the shear thickening system. Now, here what we did, we are applied the shear stress and the particles are adhered together. Once you remove the shear stress, again, this all dispersion becomes the normal. That means they becomes their original state. They becomes their original state. Are you understanding everyone? Are you understanding everyone? They are adhered together. The particles are adhered together. And when you remove this shear stress, the particles becomes the individual only. They come back to their original state. They come back to the original state. Here N is, in the dilatant flow, N value always less than 1. Always less than 1. Right? Always what? Less than 1 in the N value. Means, whatever the shear stress we are applying, the shear stress will be less than 1. 0.8, 0.5, 0.6. If it is coming to the 1, N value, whenever it will comes to the 1, the material start behaving like a Newtonian. The material start behaving like a Newtonian. When N value approaches the 1, they start behaving like a Newtonian. When the N value less than 1, they are under the dilatant flow only. They are under the dilatant flow only. This is what making the difference between these two things. This is what make difference between the two things. Now, example for the dilatant flow. Can you tell me, deflocculated suspension will show or flocculated suspension will show? Obviously, here deflocculated system. Deflocculated suspension generally will shows the dilatant flow. But not all deflocculated, wherever the having the 50% of the solid content are greater than 50%. 50% or greater than 50% of the solid content is present, then only it will shows the dilatant flow. Examples are very, very important here. Flocculated suspension, that will be come under the plastic flow. They are having the flocks. Dilatant deflocculated suspension, they don't have the flocks, but after applying the stress, they are adhering. This is plastic. This is dilatant. That's why viscosity increases in the dilatant flow. Shear thickening. Here breaking. Here we are breaking. Are you understanding? Same in the pseudoplastic system. What is that? Polymers. Polymeric solution. Here also polymeric solution breaking. But What is the difference between these three materials? Understand. After breaking, we required some force. After breaking, we required some force. Then the flow is starting. Here, there is a no strong interaction. There is a initially only flow is there. Here also initially flow is there. Initially here also flow is there. Okay. So this is what the difference between the plastic, pseudoplastic, dilatant flow. I hope you all of them concept is very clear. What is happening in the plastic flow, pseudoplastic flow and dilatant flow. I don't think so anyone feels the anything difficulty. Now your concept is crystal clear. Initially no flow, that is in the plastic flow. Pseudoplastic and dilatant flow, initially flow is there, but not a greater flow, but there is a flow. But in the pseudoplastic flow, how they behave? Yes, when you applied the shear stress, the viscosities decreases. The viscosities decreases. Okay. In the dilatant flow, when you applied the shear stress, the viscosities increases. Here, there is a no bonding. Here, there is a little bit of the bonding. Polymeric solution. By making the polymeric solution means already you broken some bonds. Already you broken some bonds. That's why you made the polymeric solution. Okay. So that is what the differences are. I hope all of them clear. And the next part 2 of rheology we'll see in the next video. Thank you so much everyone.